loud levels.
How about, this is L equals 1. How about L equals 2? Is L equals 2 allowed or forbidden? 1. Is it allowed when n is equal to 2? No, it's forbidden. If we go to, so we have to go up to the next n. The next n value is going to be n equals 3. When n is equal to 3, what are my allowed L values? L can be 0. L can be 1. Can L be 2? Yeah. How about can L be 3? No. It's forbidden. That would violate the Schrodinger equation. And so we're going to have to stop here. And so let's figure out all the allowed ones. So if n is equal to 3, L is equal to 0, then we have a 3, 0. And then what is the m value in Ln? M is going to be equal to 0. So this is a 3, 0, 0, aka a 3s orbital. 3s orbital. So the 3s orbital was shown here. That big one there. And then L can be 1, and so the 3 1s are going to be a little higher in energy. It's a little higher in energy, like this. Here. And so we're going to get 3 1. Now what are the m values? M is going to go from minus L to plus L. So it's going to go from minus 1. This will be 3, 1, 1, minus 1. 3, 1, minus 1, sorry. And then m can be 0. So this will be 3, 1, 0. And L can be a plus 1. So this will be a 3, 1, 1. And so again, this could be the 3px, 3py, 3pz. These 3 orbitals are called the 3p orbitals here. But we also have this allowed, L equals 2. If we have L equals 2 allowed, then we're going to have 3, 2, what? Do you see the pattern? It's going to be 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. And so altogether, how many are there? There are 5. Do you know what we call these? These are the m values here. M ranges from minus 2, minus 1, 0, plus 1, plus 2. These are called the 3D orbitals. That's what it's L equals 2. There are additional mathematical patterns here. You might notice, you might not. So for n equals 1, how many orbitals do we have total with n equals 1? Just 1. If n equals 2, how many total orbitals are there with n equals 2? Well, 1 plus 3 is 4. When n equals 3, how many total orbitals are there? 1 plus 3 is 4, plus 5 is 9. 9 total orbitals. Do you see a mathematical pattern? It's n squared. There's going to be n squared orbitals. When n equals 4, how many orbitals are there? 16. Is that what we see? Yeah, that's what we see. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16 orbitals. There's another pattern here. When L is equal to 0, we have 1 m value. When L is equal to 1, we have 3 m values. When L is equal to 2, we have 5 m values. When L is equal to 3, we have 1, 2, 3, 4, 5, 6, 7, 7. Do you see a mathematical pattern there? Yeah, or another one. 1, 3, 5, 7, 9. Yeah, maybe every odd. Next one would be 11. But let's say, okay, let me give you this. L is equal to 978. How many are there? Well, you go 1, 3, 5, 7. Is that how you're going to do it? No, that's not how you're going to do it. You've got to think of another way to do it. So try to think of another mathematical pattern that might be able to. I can tell you how many there are. If L is equal to 978, I might be able to count them. So I'll go 978 is 1, 977. I'm going from minus. So minus 978, minus 977, minus 976, minus 975. Do you want to do that? I don't want to do that either. But it's a very simple pattern. Do you see it? You have a negative bunch of numbers, and you have a positive bunch of numbers, and you have a 0. So how many negative bunch of numbers do you have? Well, let's pick L equals 2. How many negative bunch of numbers do you have? 2. How many positive bunch of numbers do you have? 2. And 1 0. And so the pattern is this. The mathematical equation is how many m values? The number of m values is equal to 2 times L plus 1. 2L plus 1. And so if I'm at 978, I don't have to count it. I have 978 negative values. I have 978 positive values plus the 0. And that's going to tell me how many I have. Because if there's an infinite number of orbitals for the hydrogen atom, that's a lot, right? And we don't want to memorize that many. And so, so it's easy. If we know the mathematical pattern, then it's easy. Let's say I'm at n equals 5. How many total orbitals do I expect to find? 25. If I'm at n equals 10, how many? 100. If I'm at n equals 100, n equals 1,000. A million. A million orbitals. A million orbitals. Can you figure them all out? Yeah, we can figure them all out. It just takes some time. Right? And so this is the power. Rather than memorizing some thing like that, we can figure it out. And so this is why we want to know the mathematical pattern, so we can figure such things out. And so an example of this would be this. Is a 6H orbital allowed or forbidden? A 6H orbital allowed or forbidden? And so what we have to do is we have to figure out what L value that is equal to. And so we know that when we look at the L's, we got 0, 1, 2, 3, 4, 5, 6. So L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F. Once we hit F, then it goes alphabetical. And so after F, we'll have G, we'll have H. Is a 6H orbital allowed? The answer is yes. Because L can have all values up to a max of n minus 1. Let's math. Is a 6I orbital allowed? No, it's forbidden. Okay, if a 6H orbital is allowed, how many orbitals are in a 6H? We call that a subshell. I'll talk about it in just a moment. So how many individual orbitals do I have? In other words, how many m values do I have? I'll have 5 negative m values, 5 positive m values, and 1 extra, the 0. So that means I'm going to have a total of 11 orbitals. And so, yes, in the 6H, I expect to see 11 allowed orbitals. What are they? Well, they're going to be 6, 5, negative 5, 6, 5, negative 4, 6, 5, negative 3, etc. And so using this, we can generate the entire orbital energy level diagram if we wanted to. But there's something funky about this one. Do you see what's happening here? We go 3s, 3p, 3d, but what's happening with this 4s? 4s is kind of poking down in there. Not only that, we go 4s, 4p, but what happens with this 5s? The 5s is kind of poking down in there as well. And so, although this diagram is hard to see, I'm going to redo this diagram. Let's clean up this diagram without all the numbers. This is going to be called the orbital energy level diagram for multi-electron species. Orbital energy diagram, orbital energy level diagram for multi-electron species. I'm going to skip the multi-electron part for right now. And so what we do is we plot some arbitrary energy axis on the y, and then we'll start off. The lowest energy orbital is going to be the 1s orbital, like this. And then that's going to be followed by the 2s, which is followed by the 2p, but the 2p aren't that much higher. Followed by the 3s. Now, there's a big jump between the 1s and the 2s. And so what we're going to have are shells, energy levels. So this is the first shell. A shell of orbitals is the set of orbitals with similar energies. So this 1s, there's only one orbital in the first shell, and that's the 1s orbital. The next shell will consist of 4 orbitals, the 2s and the 2p. So this will be the second shell. In the second shell, there are 2 subshells. And so we have the 2s subshell and the 2p subshell. We can also call this energy level, first level. In the second level, we have 2 sublevels, the s sublevel and the p sublevel. In the third, we just have the 3s and the 3p. The 3d, however, are not part of the third shell. The 3ds end up going into the next shell. And so we're going to split these here. And so the 3s and the 3p, this is going to go in the third shell. And then in the fourth shell, it's going to be interesting. It's just going to be the 4s and then the 3d. There are 5 of them. And then the 4p. There are 3 of these. And so it's going to go like this. It's going to go 4s, 3d, 4p in terms of the energy. And this would be the fourth shell. Each of these orbitals is defined by 3 numbers, each of them. So, what's this orbital called? Those are 3D, but there are 5 of them, so we want to name each one. This is like if you have 5 pet dogs. If you have 5 pet dogs, do you name each dog 3D? No, you'd have an individual name for each dog. So this second dog you would call the 3, 2, 3, 2, negative 1. So this would be 3, 2, negative 1. 3, 2, negative 1, 3, 2, negative 1. And so we can name each of these because each of these orbitals is defined by N, L, and M. They'll have a unique N, L, and M. Now let's take a look at the energy level diagram in your book. What is funny about the energy level diagram in your book? Well, it's missing the 1s and the 2s and the 2p. At least it has the 3s and the... But what else is kind of funny? There's a huge gap between the 3s and the 3p, but really there isn't a huge gap. What else is funny? What's funny about the 3p? Compare it to the 3p's I have and their 3p. What's different? It's on top of the 3s, but you know that doesn't matter. I only offset it because I want to keep the L separate. That's all. But really, it's on top. It doesn't matter if it's on top or to the side. It's fine. But how many 3p orbitals are there? 3. How many 3p orbitals do they have? 1. Figure 1114, do not look at that figure. Do not look at it, do not memorize it, do nothing with figure 1114. Figure 1114 is garbage. If you some people do memorize this, but if you have this memorized in Chem 1A, you're going to be in trouble because you're going to have to unlearn it, and it's better not to learn it in the first place and unlearn it later. So 1114, this is useless. This figure 1114 is worthless. So forget it. This is the Chem 1A book, so let's take a look. Quantum mechanics is chapter 8, Chem 1A. Talk about light, wave, photon, spectra, Bohr model. Same stuff. Wave particle duality, Heisenberg. This Heisenberg guy. Waves. Quantum mechanics. There are actually 2 of these energy level diagrams. Hydrogen has a very interesting one because hydrogen has what we call degeneracy. That is, all the n equals 2 orbitals of the same energy. All the n equals 3 orbitals of the same energy. Now this is for hydrogen. And so it gives us a very simple pattern. But when we get to multi-electron species, then there's some splitting in the the energies. Splitting means they're no longer degenerate. You don't have to know this. What you should know is the multi-electron diagram. So we'll take a look at. These are shapes of orbitals. So do you see this diagram on the right? You need to know this. So we got the 1s followed by the 2s and 2p. Do you see the 2s and 2p are kind of close in energy? So we got the first shell, we got the second shell, we got the third shell, although this is tricky because they don't show enough. The third shell really consists of just the 3s and the 3d actually get pushed into the fourth shell. So this drawing's not detailed enough in Chem 1A. So what we need to do is we need to, these are the loud states with electrons, so what we need to do is we need to put electrons in these orbitals. So let's do that next. We need to put electrons. Well, actually, there's one more thing I forgot to do. And that is this energy. You know, this energy ordering is best remembered like this. You know, in other words, p orbitals are higher in energy than s orbitals, d orbitals are higher in energy than p orbitals, f orbitals are higher in energy. It goes like that. So then there are bigger jumps. A 4 orbital is higher in energy than a 3, which is higher in energy than a 2, which is higher in energy than 1. We can get an idea of the energies and also figure out when things get bumped around by using this pyramid. We go 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g. And then what we do is this is the energy. And so this is used to predict the energy. So we start off with 1s, and then we go to 2s. After 2s comes 2p, followed by 3s. 3s goes to 3p, which goes to 4s, not 3d. 3d goes to 4p, which goes to 5s. And so this is in terms of increasing energy. So that's a pattern. That pattern is not 100%, but it's helpful. These are what the d orbitals look like. The d orbitals have these clover leaf type shapes, more complex. You should kind of know what an s orbital looks like. It's just a ball, and a p orbital. The d orbitals you don't need. F orbitals are even more complex. All right, when we put electrons in atoms, then we have to worry about something called electron spin. Okay, so let's. What we're going to do is we're going to fill the orbitals with electrons. When we fill orbitals with electrons, we have to watch out for electron spin. And the electrons act like little magnets. So if there's an electron here, this little magnet could have the north pole up, or this little magnet could have the north pole down. So the north pole is pointed up. That's actually spin, which we call S. There are two spin states. There's +1/2 and -1/2. Depends on the orientation. And so if it's spin up like this, we'll call it +1/2. If it's spin down like this, we'll call it -1/2. And there are only two spin orientations on here. Which brings us to something called the Pauli exclusion principle. The Pauli exclusion principle states that no two electrons in an atom can have the same set of 4 quantum numbers, N, L, M, and S. I'm going to leave this diagram out, but let's take a look at an example here. Let's look at hydrogen. Hydrogen, what we're going to do is something called the ground state. The ground state is the lowest energy possible. Lowest energy possible. And so this hydrogen, hydrogen has 1 electron. And so what we want to do is we want to put that 1 electron in the lowest energy orbital possible. What is it? What is the lowest energy orbital possible? The 2s or the 1s? The 1s. And so we're going to put it in the 1s orbital. Now we have a choice. We could put it spin up, or we could put it spin down. It doesn't matter if it's spin up or spin down because, you know, does the hydrogen atom care which side is up? Like a little. It doesn't know if it's upside down or right side up, does it? It doesn't know unless it's in a magnet. But anyway, going back to this, what do we call this electron here? This electron is going to be called the orbital is defined by 3 quantum numbers, 1, 0, 0. And the electron is defined by 1 quantum number. So this would be called the 1, 0, 0 plus 1/2 electron. The first 3 are the orbital. The last one is the spin. And so N, L, and M are the address. S is the orientation of the spin. Over here, this electron has the same address. It's a 1, 0, 0, but the orientation of the spin is opposite. So this would be a 1, 0, 0 minus 1/2 electron. So either one's fine for the hydrogen. Of course, this electron can get excited. I'm going to stop, writing the E. I'll just write the arrow. Because I have the electron arrow. If we go to helium, helium has 2 electrons. So what I could do is this. I could try to put both electrons in the same orbital, the same address. Can that happen? Yes, that can happen. And so I'll put both electrons in one end. And so if I did that, then this electron would be called what? This electron would be a 1, 0, 0 plus 1/2. How about this electron here? What would this electron be called? 1, 0, 0, but it's spin up plus 1/2. This is forbidden. Why? Because this would violate the Pauli exclusion principle. So maybe we can't put 2 electrons. Well, it turns out we can't put 2 electrons in here as long as one is spin up and the other is spin down. And so this one will be a 1, 0, 0 plus 1/2, and this one will be a 1, 0, 0 minus 1/2. And then we're good. And so helium, that's where the electrons would go. We'd have 2 electrons in that spherical orbital. Okay, after helium comes what element? After helium comes lithium. Lithium has 3 electrons. So let's try to put all 3 into the 1s orbital. If we put all 3 into the 1s orbital, maybe we'll go spin up, spin down, spin up. We'll just alternate the spin. Spin up, spin down, spin up. Is that okay? No. It's not okay because the first and the third electron will have the same set of 4 quantum numbers. So this violates the Pauli exclusion principle. Violates Pauli. So we can't put 3. So what Pauli says is this. Pauli exclusion principle says that the max number of electrons is 2 per orbital. In other words, 2 electrons per orbital. So one has to be spin up, the other has to be spin down. And so if we have lithium with 3 electrons, then 2 of them can go in the 1s orbital. So we'll put 1 spin up, 1 spin down. The third one has to go where? Well, what's the next available orbital? The 2s. And so it could go spin up or spin down in the 2s. It doesn't matter. If it goes spin up in the 2s, what do we call that electron? That would be called the 2, 0, 0, plus 1/2. And then this one would be the, 2, 0, 0, minus 1/2. That would be it. Okay, so what we're going to do is we're going to, do this. So, for example, here, what is that electron? There. What did you get? 3, 1, 1, minus 1/2. Is that what others got? Yeah? Okay, good. This would be called an excited state. So let's say the electron from hydrogen got popped up to here. That would be an excited state. What we're interested in is ground state, the lowest. So this is not going to stay excited forever. Eventually this could drop down. If this drops down, does it emit any color of light? Can it drop down any amount it wants? Drop down a little bit, or no, it's going to drop down to the next level. And in that process, it's going to emit light. And so in hydrogen, it drops from the third to the second, we call it a red photon. Although the energy level diagram looks a little different than this. All right, so what we're going to do is this. We're going to fill this in for some elements here. We're going to do that. So hydrogen, we'll go spin up just because it's convenient. 1 electron, like this. Helium, 2 electrons, look like that. Lithium, 3 electrons. After lithium comes beryllium. And then I go to boron. Now boron, does it matter which of the 2 P's I pick? It doesn't matter, at all. I can pick any of these 3. It doesn't matter. But we just picked the first one. So this is boron. Carbon. Okay, now I have a choice. For carbon, where should I put the 4th electron? Where do you think the 4th electron should go? You tell me, and I'll put it there. Tell me where the 4th electron goes. No, it's not a trick question. I haven't told you the other rules yet, and so there's no right or wrong answer. Just tell me if you were to guess, where would you guess you'd put the fourth electron? Would you guess here? Or 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 maybe like this? How should you do it? Put it next to the first one? Okay. If you put it here, then you're in violation. You're in violation of Hund's rule. I haven't talked about Hund's rule, but now we have to talk about Hund's rule. Hund's rule states this. If you have a series of orbitals that have the same energy, all three of these 2p orbitals have exactly the same energy. We call it energetically degenerate orbitals. And so energetically degenerate orbitals are filled singly, or one at a time. One at a time. Okay, so we fill it one at a time, but we have a choice. We could do what we call parallel spin, like this, or we could do anti-parallel spin, like this. What would you guess? Should we fill it parallel spin or anti-parallel spin? Parallel spin? Anti-parallel? No idea? My guess would be anti-parallel, because if you play with magnets, you know, the North Pole and South Pole like to match up. But it turns out it's parallel spin. And so these are filled one at a time with parallel spin. And so it doesn't matter if I pick the second or the third, because they're all orthogonal to each other. But we just pick the second just because it's next in line. And so we could label these, you know, for example, what's this first electron labeled as? This would be a 2, 1, negative 1, plus 1/2. What's this one? 2, 1, 0. Okay, this is carbon. Nitrogen, where would we put the next electron? We put it here. Parallel or anti-parallel? Parallel. And that satisfies Hund's law. And this electron would be called 2, 1. Yeah. Now, that's nitrogen. What comes after nitrogen? Oxygen. Oxygen, this one would be a 2, 1, negative 1, minus 1/2. After oxygen comes fluorine. Here we have to pair it because there's no other choice. We got to pair it. And so fluorine, and finally, what's after fluorine? Neon. And so when we fill the second shell, if we fill it, we're at neon. If we fill the first shell, we're at helium. If we fill the third shell, we're going to be at argon. If we fill the fourth shell, we're going to be at krypton. And so actually we're going to fill the third shell. When we fill the third shell, it's going to fill like this. 1, 2, 3, 4, 5, 6, 7, 8. So now we're at argon. And so let's go from argon. After argon, the element is potassium. So potassium is going to have 1 electron in the 4s. Okay, then after potassium comes magnesium. Now, what charge does potassium like? Potassium ion. +1. So if potassium loses 1 electron, and you look at the remaining electrons, well, the remaining electrons are going to have all the way up to the 3rd shell filled. And so potassium's like this. Magnesium is going to have another electron here. It's magnesium. And then, not potassium, calcium, sorry. Potassium to calcium. What comes after calcium? Scandium. So, but scandium's going to start filling the D's here. So this is scandium, and then what's next? Titanium, vanadium, chromium. All right, I'm going to stop here at chromium because something odd happens with chromium. This is what we expect for chromium. We expect 2 electrons in the 4s and 4 electrons in the 3d. But the 3d orbitals, if you look at all the 3d orbitals, then it's like a ball. And so this is like, has to do with symmetry. If you have half a cake, you know, how do you visualize half a cake? Or if you have half a cake, let's say it's a round cake like this, how do you visualize half a cake? You just cut it down the middle. That's your half a cake, right? That's your half a cake. But the way we visualize half a cake is different. When I visualize half a cake using orbitals like this, then I visualize cutting it like this. So let's just take off half the cake here. And so this is my half a cake here. So what's the difference? What's the difference is the symmetry. Oh, the symmetry is different. The shape. And so what happens here is this. There's advantage to having what we call spherical symmetry. And this is like this. This is almost half a cake, like this, except this cake has 1 slice cut out of it. One slice cut out of it, right? That's missing there. Otherwise, we'd have a full half cake. A full half cake has some advantages in terms of symmetry. And so a weird thing happens with chromium, and that is, and it just happens with chromium and a couple of others, that is one of these 4s's pops up here. And so it's going to pop up a little bit in energy, but what it's going to do is it's going to fill the remaining slice out of here and create this symmetric half cake. And so what we're going to get is this, a half-filled d orbital. A half-filled d orbital is good because it has this type of symmetry. But it's going to cost because we have to take a slice from the S. But if we take a slice from an S, it's still spherically symmetric. And so an S is not as critical. We're going to talk more about this, but I thought, it's kind of weird and it's kind of confusing initially, but we'll just mention it now. Okay, I'm going to stop here.